Let's talk about the continued evolution of fiber demand and the exponential growth of fiber demand and connectivity in the data center. Traditional connector types aren't quite supporting it anymore from a density perspective. What's driving that, do you think?
It's the amount of fiber. I mean, we talk about in an AI data center, 4 to 8 times the amount of fiber in a traditional cloud data center.
Okay.
So if we're installing 4 to 8 times, do we have enough real estate to now physically locate 4 to 8 times the amount of fiber?
Okay.
In a panel? And the answer is no. Mm-hmm. A traditional LC, which is what we typically see, we plug this into a server or
mm-hmm.
a switch. Fine, that's good. But the fact that we're running up to 1,728 fibers, up to 3456 fibers in a single 1U panel, mm-hmm. the most LCs you can put in that same 1U is 192 fibers.
Okay.
So think about it, 192 fibers versus 3,456 fibers in the same space. How can you do that?
Yeah.
So in 2016, the connector manufacturers, the two largest ones, US Connect and Senko, mm-hmm. Started developing what's called the very small form factor connector, or VSFF.
Okay.
And the idea of those connectors is, how can we take a standard duplex connector that's this size, right, and repackage it into a connector that is this size.
Okay.
Approximately 1/3 the size of a LC footprint.
Okay.
Which means I can now, for a duplex connection where this module, the maximum was 16 fibers with mm-hmm. LCs, with the VSFF connector, we can put 18 connectors for 36 fibers in each module if we're doing duplex.
Okay.
Now, what both US Connect and Senko have created is a 16 fiber single connector version. Okay. So now each of these connectors supports 16 fibers. Mm-hmm. There's 18 connectors per module, which gets us a density of 288 fibers in a single module versus 16 that you would have with the LCs.
So 288 fibers in that footprint that can be easily pulled in with a bullet train system.
Yes.
And installed very quickly.
Yes.
Wow. Okay.
And 12 of these modules per 1U panel. So now we're talking 12 times 288, which is 3456 in a 1U. So from a connector type, we've talked about LCs. We've talked about the very small form factor connectors, which is the MMC or SNMT. We've talked a little bit about the MPO, mm-hmm. The multi-fiber push-on connector, the MPO, the traditional interface into a transceiver, mm-hmm. right? And the typical MPO is an MPO 12, means 12 fibers per connector. Well, QSFP, quad small form factor connector, interface on a transceiver, uses 8 fibers. Mm-hmm. You can still use a 12 fiber MPO connector, just terminate 8 fibers in it. Mm-hmm. But what we're seeing now is that as the densities increase because of the fiber needs for the AI data centers, we're now seeing those MPOs scale from an MPO 8 or 12 to an MPO 16. Mm-hmm. So 16 fibers in a single MPO, which is the same as your VSFF's 16 fiber. 16 fiber makes sense because it's done in terms of base 8, mm-hmm. right? And base 8 being a QSFP. Dual base 8 fits into 16 very well. So we're seeing a lot of cable construction as well as connectorization done in groups of 16.
Gotcha. Makes sense.
What's happening in the market from a demand perspective and supply?
Yeah, that's a great point. I've been talking to folks for months now that, something's got to give, right? You can't continue to increase demand without scaling supply significantly. And what we're seeing in the market is the supply hasn't scaled with demand, which is going to create significant constraints from a connectivity perspective and from an availability perspective, which obviously rolls downstream to project deployment and eventually turn up, which impacts revenue.
I mean, I know specifically of a case where a data center engineer did his design in the data center, did it around the MPO 16. When it came time to deploy the data center, the MPO 16 there was a shortage of, and the whole thing had to be redesigned around MPO 8.
Yeah.
Because of the lack of availability of the
That's
MPO 16. So you're right. Now, why do you think that demand is the supply is not keeping up with the demand? Okay. From my perspective, and I've talked to a couple of the different connector manufacturers, they're in a transition period. They're transitioning from the MPO to the VSFFs. And so now they have to try to balance how much do I make of each in order to keep up with the demand.
Yeah.
And right now that's causing a little bit of difficulty for them to do, which is creating some of these situations of having the 16 fibers not be available.
How do you think we address that as a market? You know, if you're a large data center operator, AI service provider, whatnot, how do we get ahead of that?
The only way we're going to get ahead is to standardize or specify a particular connector that wins out in the end, and then that manufacturer will license that out, and all the manufacturers will scale the production of that connector.
Gotcha. Okay.
Or we're going to have to look at different types of connectors that are available. So we know that in that particular case, it went from MPO 16 to MPO 8, right? But there's nothing to say it couldn't have went from an MPO 16 to an MMC, for example. However, the MMC is not in full production yet, so you can't do that, right? Yeah. The SNMT, same thing. So we're going to see different, I think, types of connectors coming on the market as well, right? So take, for example, the one that I have right here, right? This module has the expanded beam optics connector, or the EBO, it's referred to. Now, there's a lot of benefits to the EBO. We'll talk about that in a minute. But what this also does, by having another connector on the market, it kind of loosens up that supply and demand, right? It gives you more supply on the market. It's a different type of connector,
right? Completely
different from a typical MPO or VSFF or LC even.
Yeah.
Why or how is it different, right? That's what I ask myself.
Yeah.
So in a typical connector design in the infrastructure, your ferrules from the structured cabling that's in place and the jumper that you're installing generally make physical contact. Right. And there's a little spring in there that keeps tension on that. And so the cores line up and the light flows right through both and everything is good. Okay. Now, that's how we've been doing it forever, right? It works. It's good. The problem is that these two surfaces have to be clean. Right. If there's any dust or particulates that get in between this mated connection, it could potentially impact the transmission, the light that's going through that mated pair.
Excessive loss and reduction in performance.
Absolutely. Right. What the EBO does is the EBO actually, rather than have a physical mating, it actually lines up on top of one another. And then there's reflective surfaces that reflect the beam down into the other ferrule, and the light continues down the path.
Okay.
During that reflection that's happening, it's also widening the beam field, the light field. So by widening it, if there's any dust particulates that get in there, it's less likely that it will disrupt the light transmission that's going through.
Gotcha.
So a different way of doing it. And for high dust environments, this connector is a good connector to look at, right?
And as you mentioned, it does diversify demand.
Yes.
Right. So it should alleviate some of the constraints from a supply chain perspective. So that's all good stuff, Nathan. But when the rubber hits the road, right, it's got to be deployed.
Yes.
Let's talk a little bit about about the HyperReach platform, and really any platform that's going to be where you're going to be deploying fiber. I believe one of the unique characteristics of the HyperReach platform is its ability to support any connector type, whether it be EBO that you mentioned, VSFF, your traditional LC modules, even copper support can all be done under one platform.
That's right. The modularity is key.
Yeah.
It's key for a number of reasons. Number one, the modules themselves are all the same.
Mm-hmm.
It's just the front interface that changes, right? Which means that allows us to take the EBO, the MMC, the SNMT, copper RJ45s, and all installed in the same panel. Okay, so from that benefit, I mean, that's amazing. The platform doesn't care what type of fiber or connector you're using. The platform is going to support it.
Gotcha.
Okay. The other thing that it does for us, though, that's kind of behind the scenes that most people don't see, is we are very good at rapid prototyping and creating solutions. That is one thing that sets us apart from everybody else on the market. We have taken a request from the initial request that came in to a prototype in the hands of someone in 7 days. Okay,
Unheard of.
Unreal, right?
Yeah.
How do we do that? Because these modules are all the same from here back, that's about 85% of this product.
Right.
During development, 85% of the product doesn't change. We only have to change the front and figure out how we can squeeze as many connectors into the front of this, of any particular type of connector.
Gotcha.
So that development, and the reason we can do this so fast is we're only trying to redevelop 15% of this solution, which allows us to put any connector type that we want in this module, right? It's just a matter of how much can you put in there and what's a usable density.
Right.
So you've been talking a lot, Jeff, about the density, the high density of some of these solutions, especially the VSFFs. What's been the reaction in the market to that many connectors and trying to manage that?
Yeah, it's always a challenge, right? I mean, if you turn the clock back 20 years and, we're doing 144 fibers in a 1U, space was a concern. We doubled that. We went to 288 fibers in a 4U. Space became a bigger concern. The high density 576 fibers, even bigger concern. And now we're talking about numbers that are almost unimaginable. So it's always a concern.
What is being done to address those concerns right now from the connector manufacturers is our typical dust boot is, it's accessible, right? Trying to get a connector, like an LC connector or a group of connectors in such a small space, like take this middle one, for example, trying to get in there and manage this. What the connector manufacturers have done is they've gone away from a traditional latching mechanism that you would see in an LC connector, and they're going towards what's called a push-pull boot. The push-pull boot allows you to remove and insert the connector from a space that's about 40 to 60 millimeters from the front of the module. So now I can just kind of get in here and pull, and by pulling the boot, it delatches a connector. And then it's stiff enough that when I need to insert one, I can just push on that boot as well. So that's just a way that you no longer have to try to get your fingers in there and push things out of the way. You can just grab the push-pull boot, pull it out, and insert it.
I don't know who invented the fiber cable. I should maybe, but I don't.
I don't either.
I also don't know who came up with the idea of using base 12, but they did, and probably 40 years ago. And that's been the standard in the industry.
So what do you mean by base 12?
So from a construction cable perspective, it's typically been in multiples of 12. Above 12, that is, right? So 12, 24, 48, 96, which works great if you're talking about duplex transmission, right? But as you go to multi-fiber connectors, especially MPO and the 16 fiber VSFFs, 12 fiber doesn't work very well.
That's right.
So we're starting to see an introduction into different cable constructions.
So when we're talking about the cable subunits, right, the 12 fiber subunits that are either in a ribbon, right, or that are grouped together in loose stranded fiber in a 12 fiber tube, right, trying to connectorize an 8 fiber connector where I'm only using 8, but I still have to terminate it on a 12 fiber subunit because that's what my cable construction is, right? Now I have 4 fibers that are basically being wasted, right? So the first, it's been that way. And I understand why it's that way. Manufacturing processes, lines are stood up. It's expensive to change lines and actually do a different cable construction, especially when you're talking about ribbonization and everything that goes into building a fiber cable. But the market has spoken. The QSFP uses 8 fibers. So if I want to maximize a 96 fiber cable, and by using 8 fibers per connector, I can get 12 connectors. If I have a 12 fiber subunit, now I can only do 8 connectors, right? So 1/3 of my cable is actually being wasted. And that means in a conveyance where you're running multiple cables, that's a bigger cable taking up more space. So the market has reacted, and the cable manufacturers are initially started with 8 fiber subunits. But I think they're really pushing more towards 16 fiber subunits. So a 16 fiber ribbon, because that can be easily split in half to do 2 8 fiber connectors, right? So it allows us to have more fiber per cable, 100% utilization of that fiber, whether you're using a multi-fiber connector or you're using a duplex connector.
That's a great point.
Yeah.
You know, and those are important points from a manufacturing perspective. I like to think too about from a customer perspective of why should they care, right? Why should a data center operator care if we're using 12 fiber or 16 fiber, whatever the case might be, right? And it goes back to one, construction of the cable. You mentioned space and the conveyance. You know, with the significant amount of fiber that's being deployed to support these AI applications. I mean, you go in data centers and the basket tray is bending because of how much fiber's in there.
Yes.
Right. So a couple different things. One is obviously the diameter of the cable. Right. The fewer subunits you have in the cable, the smaller the cable can be.
Yes.
So that's one advantage. I think the other is an efficiency from manufacturing, right? As you mentioned, it's easier for a manufacturer to terminate an 8 fiber or 16 fiber connector on a 16 fiber subunit, right? Which rolls downhill from an efficiency and a cost perspective to customers, as well as speed of deployment.
That's right. In an AI data center, when we're talking 4 to 8 times the amount of fiber, that's fiber in the cable tray as well. So having our cable conveyances that are above the racks where all the cable is being run from point A to point B, that will fill that up fast, as you said. So if we can reduce the outside diameter by getting full utilization, that's one way. Right? The other way is the ribbonization process, right? So in a traditional ribbon construction, it's flat ribbons that are stacked one on top of another, right? And in a round cable, that leaves a lot of empty space, right? So what the market has developed is a different manufacturers call it a different thing. It's rollable or pliable. The way that the fiber is matrixed together, it's done in such a way that the fiber is actually pliable, right? Or flexible. So flex ribbon, pliable, which means you can now wrap the cable and you can take the fiber ribbons and you can kind of bend them around so it utilizes that full space within the cable and actually reduces the outside diameter of the cable. So 16 fiber ribbons, as you said, rollable or pliable or flex ribbon allows you to put more ribbons, more fiber in that cable in a smaller diameter, which now reduces the load in the cable conveyances.
Gotcha.
Right.
And I think that there are multiple considerations that come from that, right? There's the weight of the cable.
Yeah.
There's the space it takes. It impacts cooling and a variety of factors that go well and above beyond the capital expenditures of the fiber infrastructure into the operational efficiencies of the data center.
And I'm going to throw a curveball at you.
Yeah.
Because the other thing that's happening is when we have so much fiber in that cable tray, the cable conveyance, right? We're always trying to make it smaller.
Mm-hmm.
So what are other ways that you can make it smaller? Well, you can reduce the size of the actual fiber
Mm-hmm.
itself by putting a smaller buffer around each individual fiber.
Mm-hmm.
You can reduce it typically from what is a standard 250 micron to 200.
Mm-hmm.
50 microns doesn't sound like a whole lot of space, but when you have 3,456 fibers,
That's right.
It adds up.
Yeah.
The other thing that we do is we can reduce the space between the fibers. So usually there's a 250 micron, what we call pitch,
Mm-hmm.
or separation between the individual fibers.
Mm-hmm.
If we reduce that to 200 microns, now we further reduce the footprint of that ribbon, which means we can further reduce the outside diameter of that cable.
Okay.
But that causes challenges in the market.
Mm-hmm.
Okay. An MPO connector typically uses a 250 micron pitch.
Mm-hmm.
Okay. Which means if I have a 200 micron fiber that's going into a 250 micron pitch connector,
Mm-hmm.
it won't feed in.
Mm-hmm.
So what I have to do, this is a manufacturing thing, so doesn't impact the end user at all, but from a manufacturing thing, I have to strip off the matrix or the glue that holds the fibers together,
Mm-hmm.
and then I have to spread it out to 250 micron, rematrix it,
Mm-hmm.
glue it together, and then I can insert it into the connector.
Right.
So it's a evolution
Mm-hmm.
of the cable, and right now the connector manufacturers have to react to that cable construction.
Mm-hmm.
Whether
Right.
it's create a connector that it's a 200 micron pitch connector,
Mm-hmm.
or create processes to repitch that to 200 to 250.
And again, that all those manufacturing challenges flow downstream to the customer, right? Because you're talking about increased costs to manufacture.
Yes.
You're talking about speed and the volume that especially with the demand in the market that we're seeing, right? If you can increase efficiency 10%, that's significant
Yes.
from a demand perspective.
Absolutely.